Thank you for coming to my talk. In cupra-tes, several observable quantities exhibit crossovers to a pseudo gap as temperature is decreased or doping is decreased. It's tempting to hypothesize that these crossovers tell us something about the putative critical point in the ground state. Well, the dynamical mean field theory has shown a long time ago that several crossovers are observed above the critical endpoint of the Mott transition. And the importance of these crossovers has been emphasized by Antoine many times. The name Widom line, that is in the title, was suggested in 2005 by the Stanley Group. Here is what it looks like in water. You have a first-order transition at the pressure in the pressure temperature phase diagram that end at the critical point. If you take constant temperature cuts as a function of pressure, you find a low temperature jump, obviously, that we all know, and a higher temperature crossover. Strictly speaking, the Widom line above the critical point is the line where various extrema of thermodynamic quantities converge towards the critical point. The derivative of this, let me illustrate this. The derivative of the plot on the upper right corner appears on the lower left corner. It gives maxima of the compressibility at the Widom line that become a divergence at the critical point. And the specific heat as a function of temperature for various pressures exhibit maxima at the Widom line that become a divergence at the critical point. As I was saying, strictly speaking, the Widom line is the line where all crossovers converge. In a completely different field, I come back to it soon, like quantum chromodynamics, theory suggests in the temperature chemical potential phase diagram a critical point at the end of a first-order transition between the quark-gluon plasma and hadrons. The dotted line is a Widom line. The plot of the density of that fluid as a function of chemical potential is very similar to the density versus pressure plot in water. And the derivative of that plot that corresponds to compressibility has a maximum upon crossing the Widom line. Why is that concept useful? Let me take the QCD example. Heavy ion collision experiments can probe only the low density region of a putative critical endpoint and observe crossovers in various observables. If these crossovers are associated to a critical point, it should be possible to extrapolate them to obtain an estimate of where is the critical point and if there is one. Given that the phase diagram is universal in the eigendirections of the renormalization group, it is the link between these eigendirections and physical variables, such as temperature and chemical potential, that determines the slope of the first-order transition as well as the spread of the crossovers above the critical point. This can help to reinforce the hypothesis of the existence of the putative critical point without observing it directly. Okay. So I'm going to discuss another line that appeared in the physics of water and back to the Widom line and a link to cupra-tes, and I'll end with newer results. So especially in this area, most of what I'm going to say is unpublished. So the Frenkel line was studied by my students, Jérôme, Pierre-Olivier, and Charles David, with collaborators Olivier from the CCQ and Maxime from Trois-Rivières. Let me start with crossovers in the half-filled Hubbard model on a triangular lattice. This is a model that may apply to layered organic superconductors. The advantage is that long wavelength fluctuations associated to ordered ground states are estimated to happen at temperatures lower than the Mott transition. So we can focus on the physics of the crossover associated to the Mott transition. The method is DCA on a 6-site cluster with a CT-OX solver. I assume that everyone who follows this series of seminars is familiar with this type of approach. The phase diagram is temperature versus interaction strength. By the way, we still need to work on the precise location of all these lines, so don't take them all too seriously, but the location is still being calculated, but their existence is established. At low temperature, there's the first order Mott transition between metal at small u and insulator at large U that ends at a critical point. And there are a series of crossovers. 4 crossover lines above the critical point are shown. I will come back later to the Widom line that indicates extrema of thermodynamic quantities. The line labeled U inc for incoherent corresponds to loss of the quasi-particle peak in the single particle spectral weight. The line labeled U sigma of omega corresponds to the loss of the Drude peak. You can see the famous mid-infrared peak. The line U of sigma of T is what we call the Frenkel line. Notice that contrary to the Widom line that ends pretty quickly at high temperature, the Frenkel line continues to high temperature. This is inspired by the theory of fluids. The figure is the velocity autocorrelation function of a Lennard-Jones fluid as a function of time. In an electronic fluid, a closed relative is the Fourier transform of the optical conductivity that is related to the current correlation function. This is how it looks. As you see, like in the fluid case, that quantity can become negative, like here. In fluids, the Frenkel line is associated to the onset of oscillations instead of just, monotonous decay of the velocity correlation function.
André-Marie, just a quick question. This is obtained by analytic continuation of the imaginary time current correlator?
No, I mean, we take this object and we Fourier transform it.
Uh-huh. But the thing is CT-OX, no, you said?
Oh, you're right. Yes, sorry. Yeah, from CT-OX to this, we need to do analytic continuation. You're absolutely right.
Okay,
sorry.
Yeah.
I was still sleeping somehow. So it turns out that the retarded conductivity is just twice times a theta function, twice the Fourier transform of this object. And since the relation between applied electric field and current is through this retarded quantity, a negative thing means that the current that is related to this applied electric field flows during a certain time t in a direction opposite to the applied electric field. So this means that there is backscattering. Okay. The relevance of the Widom line in electronic fluids was worked out by Giovanni Sordi and his students, Caitlin and Lorenzo, in collaboration with Christian. This is the cluster dynamical mean field theory now, normal state, temperature doping phase diagram of the one-band Hubbard model on a square lattice that shows a first-order transition that I call the Sordi transition, separating a pseudo gap here and a correlated Fermi liquid in the ground state. There's a critical endpoint and a variety of crossovers. In particular, there's a maximum in the compressibility indicated by the upper red triangles. A prediction of this calculation. Please recall this because I will come back to that later. The figure on the right for the triangular lattice is for the triangular lattice Hubbard model, but the picture is qualitatively identical to the square lattice. I take it because it's a nice figure. So the plane far away is at half filling, and you can see interaction is increasing from right to left. The perpendicular plane indicates what happens as a function of doping. If we start from half filling, the Mott critical point here is smoothly connected to the critical point. Sorry, this appeared a bit earlier. The critical point of the Sordi transition, which is in that plane. And then the latter goes smoothly to zero as we increase the value of interactions, becoming perhaps a quantum critical point. And perhaps the analogous quantum critical point is seen in cupra-tes. This would mean that upon increasing U, the Sordi transition could be connected to this critical point. Okay, is there a link to cupra-tes? Let me get back to the theme here. So these are now 2x2 cluster dynamical mean field calculation for this value of U at finite on the square lattice, and again plotted as a function of doping. You see the Sordi transition at low temperature, and above the critical endpoint, you observe the Widom line and various crossovers. Since crossovers are defined in various ways, some of these crossovers, like the fall of the night shift, occur above the Widom line. You see, however, that all the crossovers end abruptly instead of extrapolating linearly to t equals 0. And this is what was observed experimentally later, as shown on the right-hand side. The crossovers so just drop. Can this be a manifestation? Can this manifestation of the Mott transition at finite doping, this Sordi transition, be an organizing principle of the phase diagram? The first row shows temperature doping phase diagrams. There are two things to notice. First, as interaction strength increases, here it's 6.279, from left to right, the critical point moves to lower temperature, as I suggested earlier. The crossovers are visible, but not the first order transition because QMC is not available there. The line with the night shift, this one here in orange, is still very visible. The bottom plot shows that the condensation energy to the superconducting state changes from kinetic energy driven near half filling to potential energy driven, as in BCS, away from half filling. This was observed in various experiments through some rules. The blue dots are the dynamical mean field superconducting transition temperature. This indicates the formation of pairs only. To find the actual TC, you need to take into account Kostelis-Thouless physics, especially in the underdoped regime. Indeed, as you can see, the superfluid stiffness as a function of electron density at 0 temperature vanishes at half filling, or vanishes as half filling is approached. This is what leads to crystallis physics in the underdope regime and restores the dome shape of the transition. For the rest of this talk, I will focus on the compressibility maximum that was predicted to occur along the Widom line. So I have one more participant here, Yuri Vilk. Let's start with single-site dynamical mean field theory. On the left is the filling as a function of chemical potential for various temperatures. As you can see, the slope becomes sharper and sharper as temperature decreases. Corresponding, it's not clear here, but it appears in another plot of that paper, corresponding eventually to a divergence of the compressibility approaching n equals 1. Going to cluster dynamical mean field theory, the effect of super exchange J can be felt. The first order transition that was here between insulator and metal is moved to finite value. So it's between two metals. One is a pseudo gap, the other one is an ordinary metal. You can also see that an infinite slope of the derivative or of the compressibility as the temperature at the temperature of the critical endpoint. So as we move to a critical point by raising temperature. This is then the prediction for the compressibility as a function of chemical potential for various temperatures from CDMFT. The divergence at the critical point here, I mean, it's a log plot. I mean, it's clear that it's going to become pretty clear, pretty big. This plot of the compressibility as a function of chemical potential obtained this time from IPEPS at U equals 10 confirms this compressibility maximum. Obviously, the different values of U and so on. But on the left here, the results for the compressibility are plotted as a function of density. There is a recent preprint from Harvard that observed this phenomenon in cold atom experiments. You can see on the left how the compressibility, a maximum of compressibility as a function of temperature evolves as temperature is decreased. So this is compressibility and doping. And you can see in the middle plot how at fixed temperature, the doping where the compressibility maximum occurs changes with increasing interactions. This gives on the right a phase diagram where the pseudogap is separated from the normal metal by a compressibility maximum. Here's a comparison on the left between the cold atom data and a calculation by Yuri shown with the red line using this improved version of TPSC. The first temperature where the maximum was observed in the CDMFT calculation turns out to be the same as the one here. In the low interaction regime, the pseudogap is a precursor of the spin density wave ground state. This plot illustrates that the maximum compressibility is at a doping that corresponds closely to the place where the pseudogap disappears in the density of states. Okay, let's do that slowly. At that filling, so this is a single particle density of states as a function of frequency. At half filling, for that temperature, the pseudogap in the density of states is almost a real gap. As the whole doping increases, 13, 16, 17%, the Fermi level moves to the lower peak. It's only at 17% doping that the pseudogap has completely disappeared from the density of states. And the maximum of compressibility here is at doping 15, so somewhere here. That brings me to this recent work of the Paris group obtained with diagrammatic quantum Monte Carlo. These are interaction temperature phase diagrams obtained at 5 different temperatures, 1, 2, 3, 4, 5. In red is the pseudo-gap region. In green, a strongly correlated metal. And in blue, a Fermi liquid. The solid line is the zero temperature phase boundary between spin density wave of stripe phase and the Fermi liquid. The extrapolation to zero temperature of the phase diagram suggests that the pseudo-gap ends at this boundary and that the pseudo-gap is a precursor of that phase. What happened here? I was a bit too fast. Okay. The maximum of compressibility observed in cold atoms is indicated with these letters C here, and they correspond to TPSC. And with a few calculations with TPSC shown that this maximum is not far from that pseudo-gap phase boundary. Note that starting from the left plot, you see that the lines of constant spin correlation length are curved. At constant doping, then it means that the spin correlation length increases, then decreases as a function of interaction as one moves from U less than the Mott transition at that filling to values of U larger than those of the Mott transition at that filling. The bottom line here shows that at the compressibility maximum of the TPSC this time, the spin correlation length is larger for smaller U. Here I want to say that even if there's no phase transition in the ground state delimited by the solid line, there can still be different, although adiabatically connected physics associated with its interaction strength not large enough to lead to an insulator at that filling and those large enough. Let me illustrate this way this concept of being in the same phase, yet of feeling whether interactions are strong or weak. This is a plot at that filling, CDMFT, so temperature as a function of interaction strength. And this is a antiferromagnetic phase boundary, because it is CDMFT, that would be a crossover in a real D equal 2 model. Even though the ground state is an antiferromagnetic phase for all values of U, for values of the of U less than the Mott transition at that filling, so this is the orange line that corresponds to the normal state, if you want. The antiferromagnetic transition is potential energy driven, while it is kinetic energy driven at large U. If we stick to observables, we see that at small U, the double occupancy decreases as we enter the antiferromagnetic phase. So in reality, these are crossovers. If you look at the calculation that does not involve mean field here like this quantum Monte Carlo calculation, you see that there's no sharp drop here, but nevertheless, there's this fall. For larger U, that's the other way. You see, you follow this that has nothing to do with an antiferromagnetic transition. You see that double occupancy increases as we enter the antiferromagnetic state. So, in conclusion, I saw that I discussed that the convergence of crossover lines can indicate an underlying normal state critical point, either at finite temperature or at zero temperature. I introduced this concept of a Frenkel line. Okay, so here in that, contrary to thermodynamics, where we have some RG, here I don't know about the universality class of this in dynamics. Also, if we tried to make connection with experiments, but it turns out that all those that we found had a lot of phonons at low frequency, and then doing a Fourier transform became a nightmare. Okay, another thing I showed is that there's a compressibility maximum at doping that was predicted by Sordi in the context of his calculation. It's observed in IPEPs and in cold atoms. And the cold atom compressibility can be reproduced by TPSC+. And this compressibility maximum, where the pseudogap disappears, is consistent between various ways of looking at it, like cold atoms, diagrammatic quantum Monte Carlo that I showed, and TPSC+. So thank you very much for your attention. I'm open to questions now.
Thank you very much, André-Marie.
Can I ask a question? Can I ask a question?
Sure.
Can you hear me?
Yeah.
Yeah, I mean, I've been away from this for a long time, and by that, there are lots of experts in the audience. I mean, how much of these, Widom line and Frenkel line phenomena can one get from these mean field theories, this extended mean field theories from quantum embeddings and that Gabi keeps talking about? When you include ghosts and more of the entanglement from the bath. In other
Yeah.
words, instead of the MFT using these sort of expanded.
Yeah, that's a good question. That's a good question, and I don't know how to answer, but I know that the ghost in the end can be equivalent to the MFT if you have many, many ghosts. So the same things should be observed.
So actually, if I can comment on that, if when we're solving the cluster, embedding framework with ghost, maybe that thing would appear, because usually the ghost approach is pretty good for total energies. Well, we have some experts here. Olivier Gingras is actually working on that. But if you just do a ghost Gutzwiller in its simplest formulation,
it's probably not enough.
It eventually becomes asymptotically equivalent to DMFT, so I would not expect that to be present.
I see.
Olivier?
Excuse me if I can interrupt that one. So in DMFT, there's a compressibility divergence, but not at finite doping, but at the yeah, and there are Widom lines in DMFT. I mean,
at half filling.
At half filling, right?
Yeah.
From
yeah.
So, yeah, okay. Thank you.
So if you take clusters, then they move to away from half filling. So presumably there's a way to do a ghost Gutzwiller with clusters, no?
Yes.
In principle, yeah. Yeah. Anyhow, that's something I want to learn from the experts in this room.
Antoine?
Yes, I have I think in my view, one of the missing pieces of the puzzle currently is how all this connects to the formation of stripes below some temperature. So, whether it does or not. So we know that from the paper you mentioned, diagrammatic Monte Carlo, we know that the pseudogap becomes eventually unstable to stripe formation, at least in the simplest model with T prime equals 0. I don't think the pseudogap has anything to do with precursors of the stripes. The pseudogap has to do with short-range magnetic correlations, right? But
it depends on the value of U, right? I mean,
he may. But you know, since at this maximum of the compressibility, the charge becomes very, very soft, it is tempting to say that eventually this may have some connection that, you know, for a phase transition, which would be a first order, a finite temperature phase transition into the charge density wave state. And in connection with the recent cold atom experiment from the Harvard group, the compressibility they measure, the way they measure the compressibility may actually have some admixture also of finite Q features, because they split their trap in two and the wavelength is conspicuously close to what we expect for the stripe formation. So my question is, in methods where you can more easily look at finite Q, this could be done also in clustered MFT, but it requires calculation of the vertex and so on. But in TPSC plus, for example, it would be very interesting to look at what happens at finite Q, the Q associated with what is expected for the stripe, and see if that softness also leads to a stripe phase transition. What do you think about that?
TPSC plus is, it turns out we can extend it a little bit in the strong coupling, but it's basically a low interaction method. And in that case, the ground state is a spin density wave. So it's not inconsistent at all with being adiabatically connected to some stripes at large.
So you are at smaller coupling. The method is reliable when the coupling is small, and in that regime we don't expect stripes. That's
right.
Which is
yes, but yes. So if you look at the charge susceptibility, it turns out it's quite small. Somebody was speaking, I don't know.
Yeah, I don't know what
happened.
Yeah, so it is the charge susceptibility is quite small actually, and yeah, contrary to what I told you, there's a maximum in the charge compressibility at the same Q as the spin susceptibility. Not a minimum, but both are maximum at the same place. I will send you a plot. So Yuri made a plot yesterday.
Maybe I'll go with one more additional question then, since we have some time. So you showed that IPEPs actually nicely also displays a maximum compressibility. Is there some reasonable quantitative agreement with, semi-quantitative, of course, between the CDMFT and the IPEP thresholds?
Okay. So, I guess we have not done the calculation up to U equals 10 yet, and it will not be so reliable probably, but we can try. Regarding CDMFT, so CDMFT is really telling us about a ground state that does not exist, in the sense that it's a normal state, right? Ground state, and we know that, the true ground state will be something else, like stripes or whatever. So in principle, CDMFT tells us about the very high temperature behavior. And we have not we should do the comparison because we have some results for U all the way U equals 9 and even more. So we could look at the highest temperature where there's a correspondence with the IPEPs, but right now I don't know. Yeah.
So maybe,
but I'm sure it will deviate as we go to low temperature. Why? Because the correlation length starts to grow. So even though the pseudo gap is already opened, if you want, I mean the physics that's happening will change as the correlation length increases.
Okay. I think Henri wants to say something.
Yes.
I try to enter the game. I try to understand what do you expect for the compressibility, the large increase in compressibility that you show nearly at the position where the pseudo gap disappears. What would you see on the magnetic properties in that case? Or at least what?
Yeah, the spin fluctuations are still leading everything. So the charge is there and it's sort of following it, but it's not.
So what do you expect? What physical observable should show you the compressibility, the large change of compressibility? This is the thing I don't understand.
Well, in calculations we can have it. In experiments it's another matter. So I had some discussions with Bertrand Rollet here, who was thinking of looking at it through the penetration under the skin depth, because the screening, Thomas Fermi screening, involves the compressibility. With phonons, it's another matter because it's not the compressibility may come in the longitudinal phonons, but there are many other things and not dominating the phonon business. So up to now, the only thing we thought about was this.
How is it seen in the optical in the cold atom experiment?
That's what Antoine was saying. I mean, they change a little bit the chemical potential by splitting the thing in two, and then they look how the thing relaxes or whatever. I'm not aware of the detail actually. They are going to come here in 2 weeks and they're going to try to understand this in more detail. But
actually, incidentally, in two-dimensional systems which can be gated, there are some really nice recent experiments like graphene, TBLG, some TMDs. There's some really nice recent experiments on the direct measurements of the electronic compressibility, from Sarah Lilani in particular. So it would be wonderful to be able to do that on a system that has a Widom line.
Okay, yeah, with gate, yeah, that's a good point.
I just wonder. We have a very large anomaly in the response to impurities, which occurs there. This is an old story we have shown 20 years ago, in which an impurity gives you a change in the magnetic response, which is very large, appears like a transition when you dope. So I wondered whether it has anything to do with the response of it has to do with the response of the electron gas, of course. But would that be connected?
Good question. I don't know. I can look at that.
This is one very large singularity which is a little bit forgotten there which is a very rather old experiments on lithium impurities in IPCO, in which we see what on one side it looks like Kondo, and on the other side, no. So I wonder whether there is any connection with. It is obviously the response of the gas to the defect.
Defect. Yeah, perhaps the screening length around the charge defect could help. It's an example.
Maybe we let Luca ask a question.
Hi, André-Marie. Can you specify a little better, because I didn't quite get it, what you mean by these spin fluctuations that still drive everything? Because it seems to me, and you might remember that we have done some very similar analysis to your one band model in the two orbital case with just simple DMFT, and when we could trace back exactly the same phenomenology all the way to the half-filling Mott transition. So it seems to me that the pseudo gap, if it's really connected to the Mott transition, for me it's an inherent charge phenomenon. So what do you mean by the fact that you still the spin fluctuations drive everything?
Yeah, you're right. I mean, I'm wrong. And what I mean is what I said is valid for TPSC. So in the weak coupling limit, it's the spin that's driving everything. But you're right that the physics is different if you cross the Mott transition. And I'm sorry I didn't quote that paper. I mean, I know that paper. There are many, many papers I didn't quote again because of lack of time. But yes.
No, but it's fine. It's fine about the quoting. It's just conceptually what I mean is that if you really find correspondence between the CDMFT theory and the experiments, then somehow this really points to the fact that the pseudo gap is connected to the Mott transition at half filling, and
Yeah,
that's
and
really
I trust that for you large. And indeed, I've always thought that there's such a dichotomy that, as you say, if U is larger than the Mott transition at half filling, then the physics of the pseudo gap is really related to very short range things, and that's what the CDMFT calculations of U, of I, and other people are telling. On the other end, now what confuses me is that with TPSC we seem to be able to go more or less continuously because we're moving away from half filling, and then the doping is doing something. So I mean that's still something to be resolved.
I think what is necessary there is that the first order transition, even at finite doping, at some point becomes a crossover, even as a function of doping. So if you're far away from half filling, you will necessarily see a continuous crossover.
Yes, exactly.
No parameters.
Yes.
But we still some signs of a Widom line, even, I mean, it's not a Widom line, but a peak in compressibility, even at zero temperature, if you are after the endpoint of the first order Mott transition at finite doping.
Mm-hmm. Yes.
Okay. Thanks.
So I mean, in TPSC, I don't think there will ever be a divergence of the susceptibility of the compressibility, but there's definitely some maximum. I would be surprised if we ever find a divergence. Yes. Again, because in that theory, everything is controlled by spin.
Mm-hmm.
But again, I repeat what I said, that when U is larger than the Mott transition at half filling, then the physics is different. And that's the reason that I emphasize the fact that the correlation length, remember in this this diagrammatic quantum Monte Carlo, we said that the correlation length, if we plot doping this way and interaction this way, then the correlation length is this way. So if you move at a given doping, you see that the spin correlation length increases and then decreases, which is again a signature that perhaps the physics is switching to something else than spin.
Hmm.
Yeah, but I just want to comment that in TPAC, the same pattern observed in TPAC plus,
Yes,
that correlation length goes up, so it captures some of the strong coupling physics.
right. I showed that on one of my plots, one that I said, for U equals 369, the correlation was 5.69, and then for U larger, correlation length at the same temperature was 4. So there's still this trend a little bit.